Welcome to this problem walkthrough. Today, we're tackling problem number 1999, smallest greater multiple made of 2 digits. In this session, we'll explore the problem, break it down, and discuss various approaches to solve it. Let's dive in. The problem asks us to find the smallest integer m that satisfies 3 specific conditions. It must be greater than n, it must be a multiple of n, and it must consist of exactly 2 distinct digits. If no such number exists, we return -1. For example, if n is 7, we need to check all multiples of 7 that are greater than 7 and ensure each candidate contains only 2 distinct digits. The input n is guaranteed to be between 1 and 10,000, so we need to handle both small and large values efficiently. The output is the integer m that satisfies the conditions, or -1 when no valid number can be found. For the first example, where n is 7, the smallest multiple of 7 greater than 7 is 14. However, 14 is made up of 2 different digits, 1 and 4, and fails the requirement for exactly 2 distinct digits. Moving to the next multiple, 21 also fails this condition. Finally, we find that 77 satisfies all the requirements. It is greater than 7, a multiple of 7, and consists of only 2 distinct digits, which are both 7. Therefore, the output for this case is 77. In the second example, where n is 13, the smallest multiple greater than 13 is 26. Here, 26 has 3 distinct digits, 2, 6, and 0, which violates the 2-digit constraint. Checking further multiples, we find that all of them contain more than 2 distinct digits. As a result, there is no valid m that satisfies all the conditions. In this case, we return -1 to indicate that no solution exists. In the third example with n equal to 12, the smallest multiple greater than 12 is 24. However, 24 contains 3 distinct digits, 2, 4, and 0, which makes it invalid. Continuing to examine other multiples, we eventually find that 144 meets all the criteria. It is greater than 12, a multiple of 12, and consists of exactly 2 distinct digits, 1 and 4. Therefore, the result for this input is 144. This shows that the solution involves systematically checking multiples until all constraints are satisfied. The constraints of the problem emphasize the need for efficiency when handling values of n up to 10,000. To summarize, the output m must be greater than n, a multiple of n, and consist of exactly 2 distinct digits. Special attention should be given to edge cases, such as when n is 1, where every number greater than 1 is a valid multiple, or for large values like 10,000, where performance is critical. Additionally, cases like n equals 13 demonstrate that some inputs may have no valid solution, requiring the algorithm to correctly return -1. To efficiently verify the 2-digit constraint, we can use techniques like checking digit frequencies or utilizing sets to count unique digits in each candidate multiple. This ensures that the solution remains both correct and optimized for all inputs. To solve the problem, one approach we can consider is a brute force method. The main idea here is straightforward. We start from the smallest multiple of n that is greater than n and systematically check each candidate to determine if it meets the condition of being composed of exactly 2 distinct digits. This involves converting the number to a string, extracting its unique digits using a set, and verifying that the set has exactly 2 elements. If we find such a valid number, we return it. Otherwise, if we exhaust a reasonable range, such as up to a limit of 10⁻⁶, we return -1. While this method is simple and easy to implement, it has some drawbacks. The time complexity is proportional to both the number of candidates we check and the number of digits in each candidate, making it inefficient for large inputs. Additionally, it requires space proportional to the size of the digit set for each number checked. This simplicity comes at the cost of performance, especially when the input n is large. While the brute force approach is simple, it has significant trade-offs. Specifically, it doesn't optimize the search space, leading to inefficiencies when n is large. To address this, we can consider an optimized approach that leverages the 2-digit constraint directly. Instead of iterating through all multiples of n, we focus on generating numbers composed of 2 specific digits and check if these numbers satisfy the problem's conditions. The process involves iterating through all possible pairs of digits, d1, d2, where the 2 digits are distinct. For each pair, we generate numbers using only these digits, such as 12, 121, or 1221. Then, we check if the generated number is greater than n and divisible by n. By systematically generating candidates this way, we skip over invalid numbers and reduce unnecessary computations. Ultimately, we keep track of the smallest valid number and return it. If no valid number is found after exploring all combinations, we return -1. This approach is more targeted and efficient, as it avoids the exhaustive search of the brute force method. The optimized approach also comes with its own complexity analysis and trade-offs. In terms of time complexity, we iterate over 90 possible digit pairs because there are 10 digits and we select distinct pairs. For each pair, the number generation process involves creating numbers with varying lengths, and the divisibility check for each number takes logarithmic time based on its size. This results in an overall time complexity of 90*d* log n, where d represents the number of digits in each generated number. The space complexity is proportional to d, as we need to store the generated numbers temporarily. Although this approach is more efficient than brute force, it still depends on systematically generating numbers and can become slower for larger values of n. However, the key advantage lies in avoiding the generation of invalid candidates, making it a more practical choice for solving this problem efficiently. The chosen strategy for solving this problem is based on several key observations. First, any valid solution must be greater than n and divisible by n, which naturally constrains the search space. Second, using the two-digit constraint allows us to directly generate and validate candidates rather than relying on an exhaustive search. The problem is reframed as generating numbers with two distinct digits and verifying their validity, which is more systematic and efficient. The optimized approach was chosen because it addresses the inefficiencies of the brute force method. While the brute force approach checks every multiple of n, the optimized strategy focuses only on valid candidates by leveraging the digit constraint. This systematic generation of numbers reduces unnecessary computations, significantly improving performance for larger inputs. The trade-off is that the optimized approach requires more careful implementation, particularly in generating and validating numbers. However, the efficiency gain makes it the better choice for this problem. In summary, the optimized approach offers a structured and efficient solution to the problem. By narrowing down the search space, leveraging the two-digit constraint, and directly validating candidates, it ensures correctness while maintaining reasonable performance. This strategy avoids the inefficiencies of brute force and provides a practical way to handle larger inputs. While it is slightly more complex to implement, the benefits in terms of reduced computation and faster execution make it well suited for this problem. The key lies in balancing clarity and efficiency, ensuring that the solution remains both effective and scalable. In this problem, we are tasked with finding the smallest multiple of a given number, n, that is made up of exactly two distinct digits. For example, if n equals 7, a valid result could be 77, which is a multiple of 7 and contains only the digits 7 and 0. To tackle this, we start with a brute force approach. First, we initialize our search by calculating multiples of n, starting with m equal to n plus itself. Then, we define a helper function, has _2_ distinct digits, which will determine whether a number contains exactly two unique digits. Using this setup, we iterate through successive multiples of n, checking each one to see if it satisfies the condition of having two distinct digits. To check if a number satisfies the condition, we convert it into a string or list of digits. By using a set, we can identify the unique digits in the number, since sets automatically remove duplicates. If the set contains exactly two unique digits, then the number is valid, and we can return it as the solution. Otherwise, we increment the multiplier k, compute the next multiple of n, and repeat the process. The search continues until we find a valid result. The helper function, has _2_ distinct digits, is simple. It converts the number into a string, uses a set to find the unique digits, and returns true if the size of the set is 2. This ensures the function is efficient and easy to integrate into the main algorithm. Now, let's break down some key insights and data structures. The choice to use a set is critical because it simplifies the task of counting unique digits, as sets automatically eliminate duplicates. This makes the check for two distinct digits not only straightforward but also efficient. Another important observation is that the algorithm terminates as soon as a valid multiple is found, which is particularly advantageous for smaller values of n. Regarding data structures, the set is our primary tool for handling unique digits, while a basic loop generates the successive multiples of n systematically. Together, these ensure the algorithm is both simple and effective. Looking at the key operations and their complexities, the process of identifying two distinct digits using set (m) has a time complexity of O(d), where d is the number of digits in m. Generating each multiple requires a single multiplication, which is constant time, O(1). If we perform this operation k times, the total time for generating multiples becomes O(k). Combining these, the overall worst-case complexity is O(k*d), where k is the number of multiples checked, and d is the number of digits in the largest multiple. To optimize the algorithm, we can skip certain invalid multiples up front. For example, if n itself has more than two distinct digits, we can immediately rule out all its multiples. Furthermore, instead of converting m to a string repeatedly, we can extract its digits directly using arithmetic operations like division and modulus, which can improve efficiency. When considering edge cases, we start with small values of n, such as n equal to 1. In this case, the smallest multiple is simply n itself, as it already satisfies the condition. For large values of n, the algorithm may require more iterations to find a valid multiple, particularly if n contains digits that lead to less common combinations. Another edge case arises when n contains more than two distinct digits. Here, the algorithm ensures that only valid multiples are checked, as the condition of having exactly two distinct digits is built into the process. For example, if n equals 7, we start with m equal to 14, the smallest multiple greater than n. Checking 14, we find its unique digits are 1 and 4, which are valid, so 14 becomes our result. For another example, if n equals 23, we begin with m equal to 46, the smallest multiple of n greater than n itself. Checking 46, we find its unique digits are 4 and 6, which satisfy the condition, so 46 is returned as the result. In conclusion, the brute force approach is simple and guarantees correctness because it systematically tests each multiple. However, for larger values of n, this method may become inefficient as it requires more iterations. By applying optimizations such as skipping invalid multiples and refining how we check for two distinct digits, we can improve the algorithm's runtime performance while maintaining its accuracy. This Python implementation solves LeetCode problem number 1999, smallest greater multiple made of two digits. The goal is to find the smallest multiple of a given integer n that is composed of exactly two distinct digits. The solution is structured as a method inside the solution class. The method smallest greater multiple takes an integer n as input. First, we define a helper function, has two distinct digits. It checks whether a number has exactly two distinct digits. This function converts the number to a string, extracts its unique digits using a set, and ensures the set length equals 2. The main logic initializes multiple to n and enters a loop. Inside the loop, it checks if the current multiple satisfies the condition using has two distinct digits. If true, it returns multiple as the result. Otherwise, it increments multiple by n and continues the search. This ensures all tested values are multiples of n. The algorithm terminates as soon as it finds a valid multiple, ensuring optimal performance. This simple yet effective approach guarantees correctness while being easy to understand and implement. Here, we have the main Java method, smallest greater multiple, which is designed to find the smallest multiple of a given number n that is composed of exactly two distinct digits. The process begins by initializing a variable called multiple to the value of n. Then, we enter an infinite while loop where we check each successive multiple of n to see if it meets the criteria. This check is handled by a helper method called has two distinct digits. If the condition is satisfied, the method returns the current value of multiple. Otherwise, we increment multiple by n and continue the search. The helper method has two distinct digits is shown below the main method. It converts the given number into a string, and then uses a hash set to track the unique digits found in the number. As we iterate through each character in the string, the loop adds each digit to the set. If at any point the size of the set exceeds 2, we immediately return false, as this means the number has more than two distinct digits. The helper method concludes with a check to ensure that the set contains exactly 2 distinct digits. If this condition is met, the method returns true, confirming that the number satisfies the requirements. Moving on, the main method is included to demonstrate how the solution can be tested. Here, we create an instance of the solution class and define an example input, n equals 12. The result of calling smallest greater multiple with this input is then printed to the console. This example showcases how the implementation works in practice, allowing us to verify that the solution correctly identifies the smallest multiple of n composed of exactly 2 distinct digits. To solve this problem, we start by initializing the variable multiple to the input value n. For example 1, where n equals 7, this means multiple is initially set to 7. Next, we define a helper function called has 2 distinct digits to determine if a number contains exactly 2 distinct digits. This function works by converting the number to a string, extracting its digits, and storing them in a set. Since sets only keep unique values, the size of the set tells us how many distinct digits the number has. For multiple equals 7, converting it to a string and creating a set of its digits results in 7, which contains only 1 digit. Because of this, the function returns false. Since the condition is not met, we increment multiple by the value of n, giving us multiple equals 14. Checking 14 with the helper function, we find that converting it to a string and creating a set of its digits gives 1, 4, which contains 2 distinct digits. This satisfies the condition, so the function returns true and we conclude that 14 is the smallest multiple of 7 made up of exactly 2 distinct digits. The output for this example is 14. For example 2, where n equals 12, the process is even simpler. Setting multiple to 12 and checking it directly with the helper function shows that converting 12 to a string and creating a set of its digits results in 1, 2. Since this contains exactly 2 digits, we immediately return 12 as the output. No further increments are necessary. The output for this case is 12. For example 3, where n equals 13, we once again initialize multiple to the value of n, so multiple equals 13. When we pass 13 to the helper function has 2 distinct digits, the function converts 13 to a string and creates a set of its digits, resulting in 1, 3. This set contains exactly 2 distinct digits, so the helper function returns true. Since the condition is already satisfied, we return 13 as the smallest greater multiple of 13 made up of 2 distinct digits. First, the helper function has 2 distinct digits is critical for isolating and counting the unique digits of a number. Second, the algorithm works by incrementing multiple by n repeatedly, ensuring that every candidate is a multiple of the original number. Lastly, this method is efficient because it evaluates each multiple in increasing order, stopping as soon as the condition is met. The output for this example is 13. Now, let's take a moment to clarify the key steps of the solution. By converting the number to a string and creating a set of its characters, the function efficiently determines how many distinct digits the number contains. This systematic approach guarantees that the smallest valid result is returned. This ensures we don't waste any unnecessary computations. This approach is especially efficient for smaller values of n because the number of iterations required is proportional to the number of digits and the multiples being checked. For instance, if n is small, the valid result is often found within just a few iterations. This is because the algorithm works incrementally, starting from the smallest possible multiple n and stopping as soon as a valid number is found. While the method could require more iterations for larger values of n, the simplicity of the helper function ensures that each check is performed quickly. Overall, this solution leverages the properties of sets and modular arithmetic to find the result efficiently, making it a robust choice for solving this type of problem. To begin analyzing the time complexity, let's focus on the helper function, has 2 distinct digits. This function determines if a number is composed of exactly 2 distinct digits. The process involves 3 main operations: converting the number to a string, creating a set of its digits, and checking the size of that set. Converting the number to a string requires O(d) time, where d is the number of digits in the number. Similarly, building the set of digits also takes O(d), since each digit is processed once. Finally, checking the length of the set is a constant time operation, O(1), because the size of the set is bounded by the 10 possible digits. So, the overall time complexity of has two distinct digits is O, D. Next, we have the main loop of the function, which iterates through multiples of n. For each multiple, has two distinct digits is called to evaluate if the condition is satisfied. If the smallest valid multiple is k, then the number of iterations in this loop is proportional to k/n. Now, let's consider how the number of digits affects the time complexity of the main function. The number of digits in a number is approximately O log k, where k is the smallest valid multiple. Since has two distinct digits is called for each iteration, and each call takes O log k time, the total time complexity of the main function becomes O k/n asterisk log k. In practical terms, k grows as n increases, and the exact growth of k depends on the properties of n, such as its factors. In the worst-case scenario, where k can be significantly larger than n, the time complexity simplifies to O n asterisk log n. This simplification assumes that k is bounded by a constant factor of n in most cases, which helps us estimate the upper limit of the function's runtime. Now, shifting our focus to space complexity, let's start by analyzing the has two distinct digits helper function. This function creates a string representation of the number, which requires O, D, space, where D is the number of digits in the number. Additionally, it uses a set to store the digits, which has a maximum size of 10 since there are only 10 possible digits, 0 through 9. Therefore, the space complexity of the set is constant, O, 1. Combining these, the space complexity of has two distinct digits is O, D. For the main function, no additional data structures are used. The multiple variable is a single integer, so it requires constant space, O, 1. Altogether, the total space complexity of the solution is O, D, which is proportional to log k, as the number of digits in the largest number checked is approximately O log k. Thus, the overall space complexity is O log k. Comparing this approach to a brute force method highlights its efficiency. A brute force method would involve checking every number greater than n, not just its multiples, to determine if it meets the two-digit condition. This would result in far more iterations and a time complexity of O, k asterisk log, k, where the additional factor arises from the larger number of checks. In contrast, the current approach significantly narrows the search space by restricting checks to multiples of n, reducing the number of iterations required. This optimization leads to a more efficient time complexity of O, k/n, asterisk log, k. While the current solution is already efficient, there is still room for further optimization. For example, mathematical properties or pre-computed lists of valid two-digit numbers could be utilized to skip unnecessary checks and improve performance. When we consider the different cases for this function, the time complexity can vary. In the best case, the first multiple of n, which is n itself, already satisfies the condition. Here, the function only needs to check one number, resulting in a time complexity of O log n. In the average case, the function typically iterates through several multiples of n before finding a valid one. The exact complexity depends on the distribution of valid numbers but can be approximated as O, k/n, asterisk log, k. Finally, in the worst case, the function must iterate through many multiples of n before finding the smallest valid one. In this scenario, the time complexity reaches its upper limit of O, n asterisk log n. To summarize, the time complexity is O, k/n, asterisk log, k, in general and O, n asterisk log n, in the worst case, while the space complexity remains O, log, k, throughout all cases. When solving problems like this, there are a few common mistakes you should watch out for. First, not accounting for edge cases can often lead to unexpected bugs. For example, failing to handle scenarios like empty arrays, single-element arrays, or extreme maximum and minimum values might expose logical flaws in your implementation. Next, relying on inefficient brute force solutions without considering their time complexity can be problematic. While brute force might work for small inputs, it could result in time limit exceeded (TLE) errors when dealing with larger datasets, especially in competitive programming. Another mistake is making incorrect assumptions about the input. For instance, assuming the input is already sorted when it isn't, or assuming all values are distinct when duplicates are allowed. Always double-check the problem description for constraints. Finally, off-by-one errors are very common, particularly in iteration-based solutions. These errors often occur when index calculations are slightly off, such as confusing I with I1 in loops. Being mindful of these pitfalls can save you time and frustration. Another mistake to avoid is not validating your outputs to ensure they meet the requirements. For example, you might return an integer when the problem expects an array, or you might neglect to sort the results or remove duplicates if the problem explicitly requires it. Now, when it comes to interviews, there are a few key insights to keep in mind. First, pattern recognition is crucial. Many problems are built around recurring techniques, like the two-pointer method, sliding window, or dynamic programming. Identifying these patterns early can help you solve problems more efficiently. Also, consider the trade-offs in optimization. While an O(n)² solution might be fine for small input sizes, larger datasets often require more efficient approaches, such as O(n log n) or O(n). Lastly, communication is key during interviews. Always explain your thought process, even if you start with a brute force approach. This shows that you're not just focused on coding but also on problem solving as a whole. To strengthen your skills further, it helps to explore related problems. For instance, the two-sum problem, LeetCode 1, is a classic example of how hash maps can optimize solutions compared to brute force. Similarly, three-sum, LeetCode 15, builds on two-sum but requires careful handling of duplicates, adding a layer of complexity. Another great problem is longest substring without repeating characters, found in LeetCode 3, which demonstrates how the sliding window technique can streamline brute force solutions. Subarray sum equals k, LeetCode 560, introduces the concept of prefix sums, which is an efficient way to handle subarray calculations. Additionally, you can explore alternative approaches to problem solving. For example, divide and conquer is useful for problems with recursive properties, like binary search or merge sort. However, this approach has trade-offs, such as the risk of stack overflow with deep recursions, unless techniques like tail recursion or iterative methods are applied. Another powerful tool is dynamic programming, which is ideal for problems with overlapping subproblems, such as calculating Fibonacci numbers or solving the longest common subsequence. The trade-off here is extra space for memoization, though space optimization techniques can often help. Finally, greedy algorithms are another technique worth mastering. These are particularly effective for problems where making locally optimal choices leads to a globally optimal solution. Examples include interval scheduling or activity selection problems. However, it's important to note that greedy algorithms don't work for every scenario. They might fail for problems that require backtracking or exhaustive search to find the correct solution. Understanding when and where to use greedy algorithms is key to leveraging their efficiency effectively. Great work! We've covered the problem's smallest greater multiple made of 2 digits and walked through a solution. Remember, practice is key to mastering these concepts. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!